We take the instant speed of Google Translate, Street View, and Photos for granted. But back in 2013, the underlying complex math powering those services was keeping Google's infrastructure engineers awake at night. They ran a terrifying projection. If users spoke to their phones for just 3 minutes a day, the resulting computational demand would require Google to immediately double its global data center capacity. This would require billions of dollars in new construction and a scale of electrical power that was physically impossible to sustain. Adding more standard CPUs or GPUs provided no solution. Those chips are general-purpose processors, built with a level of flexibility that carries significant architectural baggage. They are too power-hungry and bloated to run massive neural network math efficiently. The artificial intelligence revolution was about to hit a hard physical wall. Google had to choose between abandoning its AI ambitions or inventing entirely new hardware from scratch. They chose to build. In just 15 months, a covert engineering team designed the Tensor Processing Unit, or TPU. It is an application-specific integrated circuit, a chip hardwired for one narrow task. Traditional CPUs are scalar processors, executing simple calculations one step at a time. They work like a typewriter, forcefully punching out a document character by character. The TPU functions as a matrix processor. Instead of tapping individual letters, it acts like a massive printing press, stamping an entire page of mathematical operations in a single motion. In a single clock cycle, this unit processes 65,536 8-bit multiply and add operations. By stripping away the ability to run general software, Google engineered a brute force mathematical engine capable of accelerating neural networks exponentially. This massive simultaneous calculation is made possible by an architectural design called a systolic array. On standard chips, power and time are wasted by constantly reading and writing data to memory. The systolic array solves this. This diagram shows data flowing in a continuous wave without stopping to access memory. Data flows from the left, weights load from the top. They intersect and accumulate diagonally, pulsing like a heartbeat pumping blood. We can see this targeted efficiency on the physical die. Because it ignores general-purpose tasks, the control logic, the red box, takes up barely 2% of the silicon. This leaves the massive yellow matrix multiply unit to occupy nearly a quarter of the chip. The real-world results are staggering: 15 to 30 times higher performance and 30 to 80 times higher performance per watt than contemporary chips. The true elegance of the TPU architecture is found in the general computing baggage it was designed to ignore. That 2015 chip was only the starting line. Google iterated rapidly through liquid-cooled V3 chips and eventually toward the massive supercomputers required for today's large language models. Modern versions like Ironwood and Trillium wire 9,216 chips together into clusters, capable of generating 42.5 exaflops of power. This scale is built for the current challenge of AI, inference. This is the act of serving live, accurate answers to the billions of users querying ChatGPT or Gemini every single day. The TPU architecture is built for these low-cost, low-power, and deterministic predictions, allowing Google to serve AI responses at a planetary scale. This inference power first entered the spotlight when TPUs drove AlphaGo to its victory over human world champion Lee Sedol. Every day, these chips process over 100 million Google Photos and map the world's text for Street View. While NVIDIA GPUs are famous for training models, Google's TPUs are the hidden engines driving the daily, live application of AI globally. The artificial intelligence revolution is forged in custom silicon, quietly executing billions of matrix calculations in the dark to power the modern world.